Hello YouTube viewers, welcome to my show Rocket Monday. In today's episode we're going to talk about heat shields. So let's dive right into it. Now first thing you have to understand, what is the source of this heat? Basically speed plus atmosphere equals heat. That's all you have to think about. Now, higher the speed, the hotter it gets. Now, this is not a very proportional thing. Basically, you cannot expect, like, if I'm going at 100 km per hour, I'm gonna, let's say, have 100 watts of heat. That does not mean when you go to 200 km per hour, you're gonna have 200 watts of heat. You're gonna have like 1000. So it's exponentially hotter. The faster you go, the exponentially hotter it gets. So it's a very, very serious thing, especially when you're talking about orbital speeds. And if you want to recover something, let's say, be astronauts, be it a satellite or whatever have you, you have to go through this. There is no way to way around it. And when you are talking about speeds, what kind of speed we are talking about? You are talking about bare minimum at 28,000 kilometer, anything coming from orbit, that will be bare minimum. Now, can we exceed this? Yes, we exceed this when we are coming from either from Mars or Moon. Lunar capsules generally exceeded this kind of speed. So you have to think about the source. That's the source of it, that speed, and compare the fact that Earth has an atmosphere. They create things get very hot. So then the question becomes how hot we are talking about. Now, to give you a rough context of it, think of this way. It's so hot that the moment spacecraft hits the atmosphere does not know what to do with this kind of energy. It breaks down on a molecular level. Basically, it breaks down to such a point that electron leaves the atom. So it becomes into plasma. It's ludicrously high energy situation. It's not something to be taken lightly. And not to mention, plasma is very active. You have to maintain it. However, because of our design structure and all that, we create a shock wave. Now you might be like, why would you want to create shock wave? Don't we want to break shock waves? Now, in early 60s, I'm saying early 40s, we wanted to go supersonic. The first thing we learned is that you really don't want pointy objects. So the moment people started creating supersonic test chambers, we realized you don't want pointy things. You want blunt objects. Now, benefit of that blunt object is the moment air is traveling at, like, Mach speed, Mach 1, Mach 2, Mach 3, like that, it creates a shock wave. Now, of course, you don't want your shock wave to be this far apart. So that was the early design of 1953. Then we pushed to newer designs in around 57, and then the designs that you see nowadays is basically created in 1957 for Apollo missions. Now, benefit of this design is basically it's very close. The shockwave is very close to the craft. Benefit of that, it gives you controllable. If shockwave is way outside of you, basically this is the heat shield and shockwave is here, it becomes uncontrollable. You want it to be close, so it also acts as a very good insulator, because the shockwave will divert hot gases directly away from you. So it's like maximum heating is not happening because of this. That is why we want basically blunt object. That's why all ICBM re-entry vehicles have blunt tip. You don't have to worry about shape after that, but you have to make sure it's blunt, because you can see there is a very giant curvature to this. So you can still have a shape that is like very pointy. From far it will look like pointy, but you pay attention to its nose will always be blunt. We have to have that, otherwise the shockwave will not happen. This acts as a very good diverter. So the moment you have the shockwave, every friction, that's primary friction that's happening, will go around it rather than touching you. So okay, that's happening, but why you are still getting hot? Now you have to understand, once you start to increase the speed, the temperature, the frictional based temperature, basically the convective heating, basically like boiling water kind of heat, goes up by cube. Basically anything you have, multiply by the cube. Now at high speeds, when you are talking about anything exceeding Mach 20 or 15, you have to think about something else. That's called radiation heating. Now, when I'm talking about radiation, I'm not talking about basically gamma rays or X-rays, something like that. That will happen at hyper high speed, but generally we don't even approach that. That's like heating at something at light speed. So what happens, this shock wave, this chamber becomes like a freaking microwave oven. So you get started to cook inside using infrared itself. So that becomes a very big trouble. So when you're talking about like basically Concorde was getting frictional heating. When you're talking about Blackbird, it was getting friction much hotter than Concorde, because I told you, like Concorde was Mach 2 and Blackbird was Mach 3, but the speed was cubed. So basically the friction from the speed was cubed, so it was getting much hotter. So one was like 150 degrees Celsius, another was like reaching 400 degrees Celsius. So it was getting much hotter. However, when you're talking about at this speed, the frictional heating would be like, let's say 1 megawatt. Basically the radiation heating that's touching you, that will be like 10 megawatts. So 1 to 10 ratio happens. So the faster you go, the more you have to worry about radiation rather than you have to worry about basically friction heating. And the shockwave takes care of most of the friction heating. So this becomes an even bigger problem. Like basically this blanket is cooking you inside. So it gets very hot. So why don't we use metals? Metals are the best thing we know in terms of high temperature. Now the big like in right now, if you want to buy a metal alloy that's like the baddest in terms of melting points, that's hafnium, tantalum and carbon alloy. The melting point is 3526 degrees Celsius. That's much higher than any reentry we ever experienced. Reentries generally goes from 1500 degrees Celsius to 2000 to 2500 degrees Celsius. So this is more than good enough. The reason why we don't do that is simply because you have to understand one simple concept about that. Metals have ranges of temperature. So to give you a rough context, you must have been familiar with structural steel, the steel that is used for building bridges and buildings. Now it has a melting point of 1300 degrees Celsius, basically 1100 to 1300 depending on your composition. So that's a, let's say 1000 degrees Celsius. Now here's the thing, it does not have to reach 1000 degrees Celsius to become a liquid. If you started to heat it up, let's say in case of a fire, and it reaches like 400 degrees Celsius, it starts to lose its structural integrity. Basically before 400 degrees Celsius, it's like, I'm good, I got this. Let's say you have a rod, and on top of that rod you have 10 ton. It's hot as 300 degrees Celsius. Of course it will expand, you have to worry about thermal expansion, but structurally it's like, I'm still strong enough to handle it. But the moment you start reaching that 425 degrees Celsius, structurally it starts to become weak. So it cannot handle 10 ton, it can only handle, let's say, 9 ton. So higher the temperature, the quicker it becomes weak. So you don't have to like be a scenario where it's like, oh, it has to be liquid. No, even in a solid state it could become weak. So that is why we can't basically put metal on top of that. Now that was tried, like to put metal and put so much of it that it takes a lot of energy for melting it. That was tried with mercury system. However, we quickly learned out that it's way too inefficient. It becomes way too heavy now, because let's say your heat shield is melting at, let's say, 1 ton, you put 2 tons of metal, and now you'll find it like, okay, it still becomes weak. Now you put 3 ton. Now of course there is enough thermal mass into it that it will take basically you can survive the whole re-entry without any issue. However, you wasted 3 tons. So people realize that it's better to create what we call ablative heat shield. This was the primary reason Apollo missions was successful. Now ablative heat shield is basically something different. It's like, okay, you have a shield and you burn it. Now you're like, whoa, why do you want to burn it? Don't you want to get away from heat? Well, you want to get away from heat, but relative heat. Basically, if something is 5000 degrees Celsius, compared to that 1000 degrees Celsius would be like very cool. So the idea about this is basically it will heat up from the friction. You have a shock wave that is providing you primary protection, but there is still something. It's not vacuum there. That hot place will basically force gas molecules that are trapped into this to excrete out. Now while that is happening, the gas is creating another boundary inside the shock wall and is pushing things away. Now that pushing away makes sure the inside the shock wall you are still cool. On top of that, this material will get charred. Basically it will basically how you have seen wood becoming blackish before it burns. So that is called charring. So the charring will basically inflate it. Basically it will go from 1 inch to 3 inch depending on the design, depending on the consideration. Now the charring is generally done for a reason, because the gas is making sure your friction heating is not causing too much trouble. However, there is still a lot of infrared. So charring using carbon gives you a very good shield against infrared. Basically if there is 1 inch of carbon in front of you and there is a lot of infrared, carbon is like, I got this, you don't have to worry about it. Now of course there are also other spectrum of heat also, so carbon is a very good for those sort of application. That's why we use ablative heat shield in Apollo era. Benefit super cheap, side effect use and throw. So okay, if that is use and throw, then how the heck we did it for shuttle? Now in shuttle we employed a different kind of tactics which we call thermal soak heat shields. Now these shields act on the same principle. Basically energy cannot be created nor destroyed. So somebody came up with this idea that ceramics with specific composition. Ceramic is a vague word, so don't directly try, okay, it's ceramic. Not normal ceramic will not work. It's a very specific mix of ceramic. Now in that ceramic it will act as a capacitor. Basically it can absorb insane amount of it. Basically you can pump 10 megawatts of heat into this, but it will release it very slowly. So you can heat it up in an oven or basically re-entry scenario, and it can reach as high as like 1500 degrees Celsius and all, something like that. Like that amount of heat you can pack into it, but when you are touching it, it will not burn your hand, simply because input is like, let's say, 1 megawatt per hour, output is 1 kilowatt per hour. So basically you can go through re-entry, and your basically the tiles that you see in the bottom side of basically space shuttle is still hot. Like it has the energy, but it will release it very slowly. So you can even touch it after landing it. right? You can touch it, it will not burn your hand, but it will remain warm for a very long time, like for a few days, to like slowly dump the heat away. That's the whole point. This is what we call thermal soak. Basically, energy cannot be destroyed, not destroyed. So you're like, okay, just give me the energy. So like for 8 minutes, it's absorbing the energy, and once it's once it has absorbed all the energy, shuttle is slowed down, it reaches into thicker atmosphere, it's like lands, okay, it slowly starts to give up. Basically, it's leaching the heat away, and this is very popular with ICBMs. Then we come to another technology. Now NASA many times have created multiple technologies. They have also created inflatable habitat. You can check my video about that here. They also created something better than space shuttle system, which we call PICA heat shield. Now the project was cancelled, so they were about to throw the research away, but then SpaceX comes along during the what we call the commercial resupply mission, and there are some other behind the scenes projects that have been going on to increase the collaboration. So SpaceX and NASA comes together. It's like, okay, let's not waste away our research and let's continue the PICA research. Yeah, PICA heat shield research. Now PICA heat shield is not magically better than the heat shield that is used for space shuttle. Space shuttle shield was known as Li 900, the tiles. So what it is basically 10 times cheaper. So that is the main reason why SpaceX can offer human flight for such a low cost. The heat shield is very cheap, relatively speaking. Like, it's not cheap like, okay, I can buy it for my microwave oven or my furnace or something like that, but it is relatively super cheap, and it has survived the testing and all that. And you must have seen the docking with ISS, and it survived the landing. So this shield does work. It's thoroughly tested, and they want to make it even more basically more resilient, so it can withstand more cracking and damage, because things can happen. We learned that the hard way through space shuttle, that things can happen. You have to make sure your shield is robust enough that it's like, okay, micrometeoroid, orbital debris, space junk, all that will hit it over time, and it will hit something. So you have to make sure that shield is strong enough. That is why generally heat shields are covered when you're talking about space shuttle. I'm talking about Dragon capsule. They don't jettison the like final thing unless like you are, okay, I'm about to re-enter the, okay, remove the cover. So it's like that. So that's the PICA heat shield. It's still a ceramic, still better, like more or less the same performance as basically space shuttle, but much cheaper. So this was my presentation on heat shield. I hope you liked it, learned from it. In that case, please click the like button. If you didn't like it or didn't learn from it, I would urge you to press dislike. I would urge you to press it twice to show me your extra disappointment. And please leave a comment, because I reply to all of them. Check out all these other videos, subscribe, press the bell icon if you're free. And as always, thanks for watching.